Hello folks, welcome back to my basement. I'm here today to finish example 5A for the advanced longitudinal class. We had started going through this example in class and I promised I would finish it outside of class, and so here we are. I did catch a couple of typos and things when I was just looking through this, so I've updated this and I will post the updated version of this handout and the associated M+ files when I am finished doing this recording. So as we discussed in class, these are simulated data based on real data that were part of studies I was involved with when at Penn State as a postdoc. And the two variables in the story here are risky behavior and parental monitoring. Each of these was measured approximately annually across 12 to 18-year-old girls. So we have a spaghetti plot here of changes in risky behavior as a function of age as our time one variable. We have changes in monitoring as a function of age, and then I have a scatter plot here of monitoring by risky behavior to try to get at their bivariate associations. So as we can see from the first plot here, it looks like risky behavior is increasing on average. In Chapter 7, I had gone through the process of fitting unconditional models of change and settled on a fixed quadratic random linear model for change across age and risky behavior. For monitoring, although there was no significant linear slope, there were significant random linear slope differences across girls, so we kept the random linear model for this. It did not need a quadratic. So that is the basis of the two equations in the multivariate level 1 model here. So the way I've written this is the way that it would be estimated using univariate software, in which you would have to trick it into doing a multivariate analysis by double stacking your outcomes into the same column. So this would be one Y that contains all of the outcomes for risky behavior and monitoring, in which I have these DVR and DVM dummy codes that operate like switches to control which outcome is being predicted by which term in the model. So we have a quadratic level 1 model for risky, a linear level 1 model for monitoring, and then at level 2 we have parental attitudes at age 12, centered at 4 as a time invariant predictor of everything that has a random effect associated with it. So the risky intercept, linear slope, not the quadratic slope because it's not random, and the intercept and linear slope for age with respect to monitoring. So in this model, the idea is that we would just let all of the variance components be related at each level. So we would have four U terms in the G matrix whose variance would be on the diagonal, and we'd estimate all their covariances. Likewise, the R matrix would be per person per occasion, so each occasion has two outcomes. Each of those residuals would get its own variance on the diagonal, and then there'd be a covariance on the off diagonal. So to fit that model using first multi-level SEM software, I have this code that we went over in class. So within model is referring to the residual variances at level 1. I've got 3 placeholders here to define the linear and quadratic slopes. I have the relationship at level 1 between the residuals for the same occasion to be just a covariance at this point, so they're associated, not predicted. Likewise, at level 2 here then, I have covariances among all of the random intercepts and age slopes. I have the fixed intercepts and slopes here. I have the random slope variances here. In both of these, this is for the intercepts, this is for the change slopes. Quadratic slope variance is shut off. And then I have the prediction by the time invariant predictor. And to be able to compare our results across different versions of the model, I wanted to create correlations, which would be standardized ways of expressing the relationships across variables at each level. So I asked it to take my residual covariance, which I have labeled here, and I had labeled the variances that go with it, and compute a correlation out of that covariance and the two variances, and then I did so for all of the other relationships in the G matrix as well. In the output, we get all of the covariances, variances, the relationship of attitudes as a time invariant predictor of each of my random effects. We have the fixed intercepts here. These are the fixed linear change slopes. This is the quadratic change slope that's fixed. And then these are the random effect variances for the intercepts and for the change slopes that are linear. And then down here are the correlations. And so the residual correlation at level 1 is positive, meaning that if you are Engaging in more risky behavior than your trajectory predicts at a particular occasion, you are likely being monitored more than your trajectory would predict at the same occasion. So those had a positive relationship among the residuals when within persons at level 1. There are negative relationships between the intercepts across variables and between the change slopes across variables at level 2. So the intercept in this model is at age 18. So int core refers to the correlation among the random intercepts as measured at 18. So girls who have relatively higher amounts of risky behavior than other girls at 18 concurrently also have higher amounts of monitoring at 18 than other girls. So this is a between person association. Likewise, among the change slopes, the linear change slopes to be specific, girls who had increased in risky behavior more than other girls also were likely to have decreased more in monitoring than other girls. So there's a negative association among the change slopes as well as among the intercepts. So the same model then, if we were to fit it as an undirected single level SEM using wide data, first would require us to change the data format from long to wide, and we can do that within MPlus directly. So I have my indicator for which occasion is which, but in this analysis I am going to save the exact time at which each child was measured at each occasion so that I don't have to round time into these nearest integers. I can keep it in its original unbalanced metric through the use of an option called t-scores. So this is also known as a definition variable. The idea is that it's going to take these columns of ages and apply them as individually varying factor loadings for the risky behavior change over time and the monitoring change over time. So rather than saying that these loadings have to be integers that reflect how much time has passed, they are individually varying values that allow each child to have their own time occasions, whatever they happen to be measured at. Because it's wide data, we have to tell it not to estimate the intercept for each of my observed measures from 12 to 18 for both variables. I am going to constrain the residual variances at level 1 to be one value for risky and a separate value for monitoring. I'm doing that to be consistent with how it's specified in the multi-level version, the long data format. From there, I'm taking advantage of some built-in features in MPlus with respect to how to set up my growth model. So this pipe option is a programming shortcut that allows you to make polynomial models of change. So it understands that I'm asking for the first term to be the intercept, the second term to represent linear change, and the third term to represent quadratic change in risky behavior as measured by these observed boxes. And then the at age is the use of t-scores. So the at option is telling it to use the values in these age column as individually varying factor loadings for the definition of these intercepts and change factors. So the intercepts will all have it fixed to 1 like usual. It's the change factors that need these exact time loadings. I'm doing the same thing to create an intercept and a linear change slope for monitoring. Then we're listing the fixed effects for all of those latent variables. We are listing and labeling the variances for all of those latent variables. So these are my random intercept and change slope variances. I have shut off the quadratic variance. Then we have covariances among the variance components for the same outcome, the effect of time invariant attitudes on my 4 latent variables that have a estimated variance to them, and then we have the rest of the G-matrix covariances here labeled as well. Finally, at level 1, I have the within-person association as a covariance pairwise between the same occasions. So p with means pairwise with, so it's like 12 with 12, 13 with 13, and so on. And then the common label for all of these constrains them to be equal, and it's labeled as rescov. I then did the same computation of turning those covariances into correlations so that we could get an estimate of their effect size that would transcend model specification. Finally, I have a note over here that if you had balanced time and you didn't need to use this t-scores option, this is how you would define the intercepts and slopes. So you would just provide it with the integers that you want to have the loadings convey how much time has passed relative to time 0 at each occasion. So then we get to the output for the SEM version, which is quite long. It is the same model fit, the same results as we saw within the MSEM version. And so the new parameters here are the same as well. So I'm just going to focus on the differences across models and how the relationships are specified between risky behavior and monitoring as two separate time-varying outcomes. So I'm thinking of this as monitoring as the predictor and risky behavior as the outcome, but from an estimation point of view, they're both outcomes. So I can have covariances between them, I can have directed arrows which create fixed effects, I can have whatever I like. So the things that have changed between models, which I'm doing for pedagogical demonstration purposes, is highlighted, the changes are highlighted in yellow here. So model 2A leaves the level 1 relationship between the outcomes as a covariance, but it changes 2 of the level 2 associations from covariances into directed slopes. So I've replaced the with this on here, and I've changed the labels accordingly to convey what they mean. So because at level 1 I still have just a covariance, I know that the level 2 relationships here that these fixed slopes are going to give me are the full between person relationships, not controlling for the relationship at level 1, because the relationship at level 1 is not a fixed slope, it is a covariance. So this BF int f here, this is the extent to which the monitoring intercept predicts the risky intercept. And this one here is the extent to which the monitoring change slope predicts the change slope for risky behavior. And I'm keeping the other ones as covariances for now. So to keep the results on a similar scale, I am converting what I called in the book pseudo-standardized estimates. So at level 1, I can compute a correlation like I did before. And these these numbers, by the way, are from the original undirected model in each case. And I'm creating a standardized slope by taking the unstandardized slope, multiplying it by the square root of the predictor variable, and then dividing by the square root of the outcome variable. So that's what it would be in a single level regression. Because of the way I set up the model, it makes sense to have a similar computation here. And I talk about that in chapter 9. So that is my way of taking what become unstandardized regression slopes and turning them into standardized slopes that will have the same value as the correlations that we saw in the previous undirected model. So in the output here, new parameters relative to what we had before, things that have changed, are in bold. So now we see that there is a negative fixed slope from the change slope of monitoring to the change slope of risky behavior. And we see that there is a negative fixed slope of the intercept of monitoring in predicting the intercept of risky behavior. If I take these unstandardized slopes and I standardize them against the relevant variance components from the previous model, then I end up with the exact same numbers that we saw on the previous page. So it is the same type of relationship that's being captured, just in a direction rather than as a undirected covariance. These are both between. If I do the same thing in a wide data format, so keeping the level 1 relationship as a pairwise covariance, switching the int to int and change to change relationships to become fixed slopes instead of covariances, then I end up with the same results in the SCM version as well. Just a lot more output because of the way that it's specified with separate boxes for each variable for each occasion. So these numbers then, we'll remember these. The between-person intercept relationship is negative 4.3. The between-person change-to-change relationship is negative 1.7. So on model 2B then, what I have done is swap out the level 1 association from being a covariance via with to becoming a fixed directed slope of monitoring predicting risky behavior via on, and I have labeled that as res effect as well. Because of that change, and because this level 1 slope is specified only in the within model, this relationship is within, it's among the within parts of these two variables specifically. So the latent centered within person level 1 part of these variables is what this slope is connecting. So because of that, we end up still with a between-person intercept-to-intercept effect right here, but for reasons I truly do not understand, the change-to-change slope becomes contextual instead. And I never would have known that had I not known what the answers were supposed to be from setting it up as a between-person relationship. So now what we have in the results, after standardizing to figure out what the full between person effect would be and then the standardized version of that, we have this negative 5.2 because the change to change relationship is more negative than the within level relationship by negative 5. So that pushes us from positive into negative territory, and the resulting between person change to change relationship is the minus 1.7 that we saw on the previous page. So to figure out what the change to change relationship is that exists without controlling for what's happening at level 1, we take the level 1 residual slope. So this would be like the within person slope in a regular univariate multi-level model. We add to it the contextual effect for how the change to change slope differs from the within level slope, and then we get back to the between level slope for the change to change relationship that we saw in the previous model. Complicated. In the SEM-wide version, I am attempting to do the same thing by introducing structured residuals. So there's an asymmetry in what happens here, but let me walk through the structured residuals code. So this is an older version of it that has, there's a much simpler version of the code now that exists starting in M+, I think it's 8.8, but just in case you're using this with an older version, I'm giving it to you in that way. So the first thing that I'm doing is taking the residual variances for all of my indicators, so from ages 12 to 18 for each variable, and I am moving them to brand new latent variables that each start with an F. So this is a measurement model that says make me a latent variable as indicated by risky12, fix its factor loading to 1, and then down here I am shutting off all of the corresponding old residual variances and estimating them in the new latent variables and holding them constant. So this looks like it shouldn't matter, but what I'm doing is moving the information from the observed boxes into new latent variables so that from an estimation perspective, all that M+ sees is the within person part. So the new latent variables are purely within. That means that the level 2 model is going to have a between set of relationships rather than contextual. So now the relationships among my level 1 variables are specified on the latent factor versions, because the original versions basically have lost their information to these latent factors. And I've switched from p with to p on, which means pairwise on. So 12 predicts 12, 13 predicts 13, and so forth. I end up with the same output, though, with respect to the standardized versions of the parameters and as well as the unstandardized fixed effects. And then I also have an example here in blue of if I wanted to fit a mediation type of model, I can look at between person mediation among the intercepts. So this would be X as my time invariant predictor to my mediator to my outcome. And then this would be X to my change variable to my change outcome. So just two examples of how you can ask for indirect effects among your level 2 latent variables or observed variables as you wish. So then here is the level 1 relationship as a directed slope. That's the 3.5 that we saw. These two relationships for the intercept predicting the intercept and the change slope predicting the change slope are the full between relationships. They are not contextual in this model. All right, now changing how I ask for the level 1 slope. So in the previous model, all I had was this part, meaning that I'm defining the level 1 fixed slope directly in the level 1 model, which means that it is using the within parts of the original variables to do it. In M+, when you're using maximum likelihood estimation, and you introduce a placeholder for a level 1 slope, then the random slope and the fixed slope no longer apply to just the within person part of the variable. They apply to the entire thing. So that creates a specification that is analogous to constant centering, where the level 1 relationship is only unsmushed and purely within if you include the corresponding level 2 relationship as a control, but the level 2 relationship becomes contextual. So at this point then, by moving this syntax into a placeholder notation, asking for the fixed effect, but shutting off the random effect. Theoretically, this should be the exact same model. But because of the use of the placeholder, it is flipping it from a within-between specification into a contextual within specification instead. So the change to change slope has already been contextual. Now the intercept to intercept slope becomes contextual as well. So as before, I am going to add within and contextual of each kind to create between level versions of these slopes. Note that it is the same within slope that gets added to both. So res f is the within level relationship between monitoring and risky behavior. I need that plus the intercept contextual effect to get to the full intercept slope that is between. I need the same residual relationship plus the linear change contextual relationship to get to the full between relationship between the change factors. So then in the output, you can see the numbers are quite different. So it's -7 as the intercept to intercept relationship because this is after controlling for the level 1 relationship that's in the opposite direction. So the way that I would say this is that the intercept to intercept slope is more negative than the within level relationship by almost -8. So when you add those two things back together again, you get the -4.3 that we had seen in previous models. Likewise, if I take the within level relationship, the slope to slope, change slope to change slope relationship is more negative by -5.3. If I add those two numbers together again, I get the change slope to change slope between level relationship that we saw in the previous models. So this idea of how you add things back together to figure out what they must be is how I figured this out in the first place. This model, though, does not work like this if I were to ask for Bayesian estimation instead. In that case, the level 1 variable is only the within part, and it switches back to a within-between version. So the hybrid method is what is used in ML. The latent centering only within version is what is used if you switch to Bayesian estimation. So the exact same syntax will give you two different versions of the same model. And when I figured that out, I thought I would write a paper about it so that no one else would have to try and figure it out in as much detail as I went to. If I fit the SEM version of this model, what this amounts to is forgetting to use structured residuals. So if I strip out all of that structured residual code where I transferred the information from the observed variable residuals to new latent variables and I don't transfer it, and I just specify it directly among the observed variable boxes, then what I end up with is a contextual specification. So the reason to use structured residuals is so that your level 2 relationships are all between. If you do not use structured residuals, your level 2 relationships are going to be contextual instead, at least with respect to the intercept predicting the intercept and the change slope predicting the change slope. And here's an example again of how I can ask for mediation involving those things as well. So there's my -8 and my -5, which I can add back together to get the between slopes, and they have the same standardized effect sizes as we saw in the original correlations. By popular demand, here's an example of a latent growth model with structured residuals to do a cross-lag panel type of thing among the within parts. So in this case, I had to change a few things. I'm back to using structured residuals so that my between level information comes out of the level 2 model instead of contextual. I am shutting off all the old residual variances, and I am only holding the residual variances of the new latent variables equal from 13 to 18. So I am letting occasion 12 have a different residual variance because occasion 12 is not going to be predicted by the cross-lag effects, so it should be greater given that it's unpredicted. Likewise, the covariance among the same occasion residuals at age 12 I am letting be separate from the covariance among the same occasion residuals at the later occasions because this is unpredicted, whereas this is after predicted. So it's a residual covariance specifically. Then I have my cross-lag effects. So note I have 13 to 18, P on 12 to 17. So that means 12 predicts 13, 13 predicts 14. So it's a lagged effect that I have labeled as monitoring residual to risky residual. Then I have the opposite where risky is predicting lagged monitoring. So then we have the risky residual to the monitoring residual. And then I created standardized versions of these unstandardized slopes by including the variance components from previous analyses. So this is not an equivalent model, this is a different model. And what it looks like here is that we do not have a cross-lag relationship of this times monitoring predicting next time's risky behavior, but we do have, a cross-lag relationship from this time's risky behavior predicting next time's monitoring, which is interesting because that is not in the original data. This is actually a type 1 error. I know that because I made the data. I still have my same occasion relationships, which is basically the same size as what we saw in the unconditional models with respect to the level 1 association, and the occasion 12 association is actually different in this case. My personal preference, so these are the standardized coefficients here, my personal preference is I don't like the idea of looking at a lagged relationship unless you control for the contemporaneous relationship. I think if you want to show that it really is last times x that is relevant, you need to control for this times x. That requires fitting the lag direction only in one way at a time to be able to do that. So I did it both possible ways for demonstration purposes here. So if you want to do it that way, control for the concurrent effect before addressing the lagged effect, then I have my monitoring at 12, predicting risky at 12, and so on, and then separately I have monitoring at 12, predicting risky at 13, and so on. So this one is among the same occasion residuals, not having a covariance, but having a directed slope, and then this one is the lagged effect that provides the incremental effect of the previous occasion on the current occasion. And here are the results. The concurrent effect is significant, as we have seen throughout these examples, and the relationship of monitoring predicting risky behavior in a lagged fashion looks like it's a little bit stronger than what we saw in the previous model in terms of at least the p-value. If I go the other way, it looks like then we have risky behavior predicting monitoring at the same occasion, and then this is at the lagged occasions, and we see the same pattern. It looks like the evidence actually gets a little bit stronger for a lagged relationship after controlling for the concurrent relationship, which makes sense since the current relationship would reduce the residual variance and then potentially reduce the standard errors for the lagged relationships. One last one is that if I wanted to do something like these lagged analyses using multi-level SEM in long form, so this is making use of the new what is known as dynamic SEM, which introduces time series like possibilities into these models. The trick with this is that it's allowing you to access information that's stored on a different row of the data set and potentially address differences in the temporal interval across rows. So this is using a new version of lagged effects that was just introduced within the last few years. I'm specifying within my long form multi-level model here a lagged command saying I'd like to have risky behavior at lag 1 and monitoring at lag 1 as variables that I can then access to use in my model. And I'm using them down here in the within model via this caret, the thing above the 6 on my keyboard. That indicates the within person part of the previous occasion. So it's like a latent centered lagged variable. There is another version of this model that you might see in their user manual that has an ampersand instead, I think it is. I can't remember all the symbols. I think it's an ampersand. Don't use that one. Use this carety one. So this is the lagged effect of monitoring, predicting previous monitoring on current risky behavior, and this is previous risky on current monitoring. And then I computed the standardized versions of those using the variances from the previous analyses. And the last set of results here is a comparison. So this is what I got when I did it via SEM using the structured residuals and this is what I get out of this analysis using, it's the same model, just set up with a different data structure, and it's using Bayesian analysis though, so it's going to be a little bit different, but as you can see, it converges onto pretty much the same conclusions across the two analyses, which is always comforting. So good luck as you are trying to figure out all of what is within and contextual. The key that I told my students in my class lies in the specification of the level 1 residual relationship. So let me back up here just to make that point one more time. So this spot right here, if you change this from on to with in the level 1 model, the numbers in your level 2 model that change with it must be contextual, because contextual is controlling for the level 1 relationship, whereas between is not. So if you change this from on to with and nothing happens in the level 2 model, those are between, not contextual. Hope that helps. Thanks for staying with me, and I will see folks in a few weeks after we are done with student presentations.